about the process of mapping a complex network. Usually, the goal is to draw strings between every possible connection. But early computer scientists found success by doing the opposite, looking at every individual point in total isolation. This approach became the backbone of early spam filters. To keep your inbox clean, engineers built systems that could identify junk mail simply by analyzing the specific words inside the message. On its face, this is a difficult task because human language is highly correlated. If an email contains the word free, the statistical probability of a subsequent exclamation mark is incredibly high. To calculate the exact joint probability of every interconnected word in an email, a computer would need a practically infinite amount of processing power. To create a system fast enough for the real world, researchers had to walk away from perfect logic and deliberately embrace a flawed mathematical assumption. If a model tries to account for how every single word relates to every other word, the complexity grows exponentially. Traditional statistical models quickly hit a memory limit. They cannot process this high-dimensional space without freezing or crashing the system. It's a recurring theme in machine learning. Chasing perfect mathematical accuracy often makes a system impossible to deploy. The solution started with Bayes' theorem, a mathematical framework used to update our internal probabilities based on new incoming data points. We start with a baseline probability that an email is spam, but the moment a suspicious word is identified, that input hits the scale, shifting our confidence in that label. This framework is highly accurate when handling one or two variables. However, standard math quickly breaks down when you ask it to process dozens of interdependent factors at once. Standard probability gets stuck trying to map the intricate relationships between these variables. To solve this, engineers introduced a naive shortcut. This modification relies on a strict, mathematically incorrect rule. It assumes that every single word or feature in a dataset is completely independent from all others. This chart compares the frequency of certain characters in junk mail versus regular messages. Words like free and the exclamation mark appear in spam at significantly higher rates. But here is the intentional blind spot. It treats free and the exclamation mark as isolated occurrences, multiplying their frequencies in a vacuum, ignoring that they usually appear together. Conversely, safest indicators of a regular message, like the name George or the term HP, pull the aggregate probability meter sharply back toward the safe threshold. By ignoring the reality of context, the math transforms from a nightmare of interconnected variables into a fast, simple linear equation. This is the formal directed acyclic graph for the model. The parent node at the top, yn, represents our classification, pointing down to the individual features. If you look at the row of xn circles at the bottom, there are no arrows connecting them. That empty space proves the enforced independence between the variables. This lack of connectivity allows the algorithm to simply factorize the problem into a chain of basic multiplications. This diagram describes a system that refuses to see how the world connects, which is exactly why researchers originally dubbed it idiot space. Why does an algorithm built on such a reductive, seemingly stupid assumption actually work so well? It's because of a phenomenon called overfitting. When a model is too complex, it starts memorizing the messy, highly specific patterns in its training data instead of learning the general trend. Naive Bayes' refusal to learn complex relationships acts as a shield against this. The complex, squiggly line is replaced by a simple, sturdy straight line that captures the real signal. The model succeeds by relying on the aggregate weight of dozens of weak, isolated indicators, rather than trusting a few hyper-specific combinations. The inherent mathematical error in the model is actually its greatest asset. It acts as a regularization technique that forces the system to stay simple. In data science, a flawed assumption can often be more reliable than a perfectly accurate one. Because it is fast and resists noise, naive Bayes remains a powerful baseline for modern text classification. But what if we moved away from probability entirely? What if we tried to just draw a physical line in the sand to separate our data points? Next time, we'll explore support vector machines and see how a sharp line carving through a landscape can create the perfect separator.